Scientists did not find alien plants, oceans, or little green idiots waving at a telescope. They found something much simpler, and possibly much more important: air, escaping from a rocky planet where liquid water might exist. And strangely, the fact that this atmosphere is leaking is exactly how scientists discovered it. The planet is called LHS 1140b. It belongs to a category of worlds that are becoming some of the most exciting targets in astronomy, the super-Earths. A super-Earth is a planet bigger than Earth, but smaller than icy giants like Neptune. Crucially, they are thought to be primarily rocky, not gassy. They are one of the most common types of planet discovered in the galaxy so far, which makes it all the more strange that, for reasons scientists are still debating, our own solar system doesn't have one. And LHS 1140b is a hefty example. It's about 1.7 times wider than our planet, but because it's much denser, it's over 5.5 times more massive. And it's not exactly next door. It's orbiting its star 48 light-years away. That's nearly 300 trillion miles. But what makes it so special isn't just its size, but times where it's orbiting. To put that in perspective, if you were on our fastest space probe, the Parker Solar Probe, it would still take you almost 900,000 years to get there. It sits in its star's habitable zone, often called the Goldilocks zone. It's not so close that water would boil away, and not so far that it would freeze solid. It's in that just right region, where liquid water could potentially exist on a planet's surface. But, and this is a huge but, habitable zone does not mean habitable. It's just the first, most basic requirement. You only have to look at our own neighbors to see why. Venus, Earth, and Mars are all in or near the sun's habitable zone. But one is a scorching acid bath, one is a frozen desert, and one is, well, us. The key difference maker is a thick, stable atmosphere. First, an atmosphere acts like a planetary blanket. It traps heat from the star, preventing wild temperature swings between day and night. You don't have to look far for an example. On our own moon, with no atmosphere to hold on to heat, daytime temperatures can reach a boiling 250 degrees Fahrenheit, while at night they plummet to minus 208. Second, it's a shield. It blocks harmful ultraviolet rays from the star and deflects high-energy cosmic particles that would otherwise sterilize the surface and shred any complex molecules. And third, and perhaps most importantly, it creates enough pressure for liquid water to exist. Without it, any water on the surface would instantly boil away into the vacuum of space, even if the temperature is right. So, an atmosphere is the holy grail. But that brings us to the real problem. How do you spot invisible air around a tiny dot of light nearly 300 trillion miles away? You can't see it directly. You have to look for its shadow. Scientists wait for a moment called a transit, when the planet passes directly in front of its star from our point of view. As it does, it blocks a tiny fraction of the starlight, causing the star to dim ever so slightly. This dimming is minuscule. For a planet like LHS 1140b, it's like trying to spot a gnat flying in front of a searchlight 100 miles away. But the planet itself isn't the main event. The magic happens at the edges. Just before and after the main transit, a tiny amount of starlight shines through the planet's atmosphere. As it does, the gases in that atmosphere absorb very specific colors or wavelengths of light. Think of it like a fingerprint. Each element and molecule has a unique spectral fingerprint, a specific set of colors it absorbs. Sodium absorbs a specific shade of orange. Water absorbs in the infrared. So when scientists look at the starlight filtered through the atmosphere, they don't see a complete rainbow. They see a cosmic barcode with missing lines. By matching those missing lines to the known fingerprints of different gases, they can figure out what the air is made of. And in 2024, when a team of astronomers pointed their instruments at LHS 1140b during a transit, they found a clear, unambiguous signal for helium in its upper atmosphere. Now, you might be thinking, helium? The stuff in party balloons? But for astronomers, helium is a fantastic tracer gas. It's the second lightest element, so if a planet has a substantial atmosphere, helium tends to float to the very top and form a huge, extended cloud that is much easier to detect than the denser air below. This brings us back to the paradox from the beginning. The leak isn't a sign that the planet is dying. It's the sign that it's alive. The atmosphere is so substantial that its upper layers are literally puffing off into space, and that puff is what we can see. The leak proves the reservoir exists. Even more telling is what they tend to time find. The data suggests the upper atmosphere is mostly depleted of hydrogen, the lightest element of all. This hints that LHS 1140b is not a young gas planet, but a mature world that has likely already lost its primordial hydrogen envelope, settling into a more stable, secondary atmosphere. This helium-rich outer layer is like the tip of the atmospheric iceberg. It strongly suggests the presence of a much denser atmosphere beneath it, where heavier molecules like nitrogen, oxygen, or water vapor could be hiding, held closer to the surface by the planet's strong gravity. But science is rarely that simple. The story got another twist when a different team observed the planet again a year later, in 2025. This time the helium signal had vanished. The leak had apparently stopped. This doesn't mean the atmosphere is gone. It suggests the leak itself is variable. One theory is that the star's activity could be driving the escape. A powerful solar flare or a change in the stellar wind might puff gas off the planet, a process that changes over time. It's not a steady leak, it's a gusty one. The final piece of evidence comes from its sibling. The same star system also hosts LHS 1140c, a smaller, less massive planet orbiting closer to the star. When astronomers looked at it, they found nothing. No helium, no atmosphere, just a bare rock, stripped clean by its star. This tale of two planets illustrates a crucial concept astronomers are now exploring, the Cosmic Shoreline. It's the boundary between worlds massive enough to hold onto their air for billions of years, and those that are too small and get their atmospheres blasted away. Imagine the planets on a cosmic beach. A relentless tide of stellar radiation is always trying to wash them clean. The small, lightweight planets get swept away, but the big, massive ones are heavy enough to stay put on the high ground, keeping their atmospheric blankets dry. This process is called photoevaporation. High-energy photons from the star, especially X-rays and ultraviolet light, heat up the top layers of an atmosphere. If a gas particle gets hot enough, it can reach escape velocity and fly off into space forever. And this is what makes LHS 1140b's survival so remarkable. It orbits a red dwarf star. While smaller and cooler than our sun, red dwarfs are famously violent, especially in their youth. They can unleash powerful flares and a torrent of high-energy radiation that can strip a planet bare. LHS 1140b, however, seems to be a survivor. Its high mass, over 5 times that of Earth, gives it a strong gravitational grip. Models suggest it was massive enough to weather the storm of its star's youth and hold on to a significant portion of its atmosphere for billions of years. So, let's recap. We have a rocky world in the habitable zone that has successfully held onto an atmosphere. It checks all the major boxes. This leads to the billion-dollar question: could it have liquid water? This is where we move from observation to modeling. Based on the planet's density, some scientific models suggest it could be a water world with a global ocean, potentially hundreds of miles deep. Its thick atmosphere would provide the necessary pressure to keep that water liquid. But it's crucial to be clear. This is a model, not a discovery. For now, we have no idea what the surface actually looks like. It could be a water world. It could be a dry, volcanic world. The truth is hiding under its cloudy sky. Finding out requires looking for biosignatures. These are gases that are unlikely to exist in large quantities without a biological source. On Earth, for example, the vast amount of oxygen in our air is produced by plants and algae. Finding a combination of gases like oxygen and methane on a distant world would be a staggering discovery. This helium detection is just a signpost. The real hunt is for heavier molecules trapped deeper below, like water vapor, methane, or carbon dioxide, gases far more relevant to a truly habitable world. And this is where the James Webb Space Telescope enters the story. Its unparalleled power and sensitivity to infrared light are perfectly suited to hunt for the spectral fingerprints of these heavier molecules. Because of this discovery, LHS 1140b has vaulted to the top of the observation list. It's no longer a random shot in the dark. It's a confirmed target with a known atmospheric envelope to investigate. However, even with Webb, this will be a monumental challenge. Detecting faint signals from a thick, deep atmosphere is far harder than spotting helium escaping from the top. It will require many observations over several years. Ultimately, these future studies will reveal one of two incredible outcomes: a barren world with a thin, helium-rich haze, or a planet with a deep, complex atmosphere, a true potential haven for life. The discovery of its helium halo has instantly promoted LHS 1140b from one of thousands of exoplanets to one of the most important targets for follow-up studies in the search for life. And the perfect tool for the job is already in space, the James Webb Space Telescope. Its powerful infrared instruments are uniquely sensitive to the spectral fingerprints of molecules like water, methane, and carbon dioxide. It is our best hope for peering deeper under that helium haze. So this is the story so far. A rocky super-Earth in the habitable zone of a nearby star has an atmosphere. We know it exists because we saw the helium from its outer layers leaking into space, and its sheer size allowed it to survive its star's fury, placing it on the safe side of the cosmic shoreline. We have not found life on LHS 1140b. We don't know if it has water. But for the first time, we have direct evidence that a rocky world in a habitable zone can hold onto an atmosphere. The question is no longer dürfte such worlds exist. The question is what we will find when we finally look beneath their skies. Discoveries like this are happening faster than ever. If you enjoy exploring the biggest questions in science, explained simply, consider subscribing for more.